Anti-forensics of median-filtered images using nonlinear optimization techniques. Abstract. A number of forensic approaches have been developed to identify the use of digital multimedia editing operations. In feedback, several anti-forensic operations have been designed to fool forensic algorithms. One action that has received huge attention is median filtering, since it can be used for image enhancement or anti-forensic purposes. As a conclusion, several median filtering detectors have been developed. In this paper, we propose an anti-forensic technique to disguise the use of median filtering. We do this by first state a model for an unaltered image's pixel difference distribution. We then modify a median filter image's pixel difference distribution using anti-forensic noise so that it no longer contains median filtering fingerprints. Through a series of analysis, we are able to show that our anti-forensic approach can fool existing median filtering detectors under realistic conditions. Index terms: anti-forensics, median filter, pixel difference. 1. Introduction. Due to the ease with which multimedia content can be used, measures to verify the authenticity of multimedia content are in pressing need. Some forensic part on multimedia contents have been developed to find different multimedia editing operations. For some cases, techniques are achieved to identify image resampling 1, double JPEG confining 2, contrast enhancement 3 and median filter operation 4, 5. These forensic approaches operate by detecting the forensic fingerprints left in the multimedia content by editing operations. An intelligent forger, after all, can develop anti-forensic measures in form to fool the forensic detectors. These anti-forensic measures ambition at eliminating the fingerprints introduced by multimedia editing operations. Several anti-forensic techniques have been refined for clashing operation detectors, such as extract the artifact of resizing and rotation in 6, forging the history of image compression 7, 8, histogram control 9, color filter array arrangement alteration 10, and video motion vector adjustment for frame deletion in video sequence in 11. By studying anti-forensics, we can identify the capabilities of an intelligent forger and develop measures to detect the use of anti-forensic techniques. Median filtering is an image editing operation of particular forensic significance. It is commonly used to perform several image enhancement tasks such as noise suppression and smoothing. Median filtering has the applied assets of preserving edge content due to its nonlinear nature. Newly, median filtering has been displayed to be destructive to several other image manipulation traces due to its strong nonlinearity. 6. Due to this painful nature of median filter, the median filter has been mixed into several anti-forensic approach such as in 8. Thus forensic measures on median filtering is leading because once median filter is detected by the detector, the accuracy of the image is questionable due to the possibility of other multimedia operation. Several median filter detectors have been expected in 4 and 5 for detecting median filter operations. An anti-forensic attack on median filtering detectors is of particular interest for image forgers. While median filtering is destructive to other image control fingerprints, it flags behind its own fingerprints. Grant the case that a forger applies a median filter at the end of image processing to destroy the fingerprints of previous image editing operations. The forger would then like to apply an anti-forensic technique to abolish the median filter fingerprints from the image. If it can be done, the forger can crop a forged image that is free from any image editing operation fingerprints. This approach shows that the harmful nature of median filtering form median filtering anti-forensics actual appealing to forgers. In this journal, we state a novel anti-forensic technique to remove traces of median filtering. We first ask using a generalized Gaussian distribution to model the pixel value difference delivery of an unaltered and median filtered image. We develop an estimation method to estimate a plausible pixel value difference distribution of an unaltered image given a median filtered one. Using the plausible approximated pixel value difference distribution as an objective, we estimated the noise distribution to be joined in the median filtered image and shift the pixel value change distribution to the plausibly one. Several adjusts are enforced in the noise addition algorithm to balance the attack might and the visual perception. Certainly, the anti-forensic attack is tested against a few median filter detectors and the outbreak strongly falsifies the detector in typical detection scenarios. While forward work removes element of median filter by optimally sharpening an image 12, our proposed access achieves better performance at low false alarm rates. 2. Problem formulation. We first give a brief introduction on the operation of median filter. Let xij be the pixel point value at location, I, j, of an constrained image. The identical pixel points ej in a median filtered version image is given by the point ej equals meds, xij. Here meds denoted the median filtering points operation with a square filter bay with size of s defined as. Median filter detectors. Several median filter detectors have been proposed in prior works 4, 5. Kirchner and Friedrich proposed a detector that operates based on the statistics of pixel value differences of a median filtered image and an unaltered image 4. The detector first divides the image into blocks. The pixel difference histogram in each of the block is calculated. Next, the ratio of the number of pixel differences, whose value is 0 to the number of pixel differences whose value is 1 is calculated for each block. A weighting function is applied to the value of each block to avoid statistical distortion in saturated regions, and a final measure of the strength of median filtering fingerprints is obtained. Kirchner and Friedrich also proposed using the subtractive pixel adjacency matrix, SPAM, detector which is originally developed in steganalysis in 13 for the detection of median filter operation. They first model the pixel value difference distributions in an image to be an nth-order Markov chain. The SPAM detector then uses the Markov chain transition probabilities as features vectors which is used in support vector machine. In 5, Ewan proposed a median filter detector which collects blockwise median forensic features, MFF, which are statistics based on the pixel values and its distribution in the block. Different entries of MFF is then combined heuristically to produce a new index F. A binary decision is then made according to the index F to determine whether the image has undergone median filter or not. Anti-forensic technique. Both the and SPAM detectors proposed by Kirchner and Friedrich detect median filtering by capturing features of the distribution of an image's pixel value differences. Furthermore, several of the detection features proposed by Ewan implicitly capture information about an image's pixel difference distribution. As a result, an anti-forensic attack on median filter detector should ensure that the pixel difference distribution of an anti-forensically modified image resembles one that is from an unaltered image. Since a forger does not know whether a median filtering detection technique will examine the horizontal or vertical pixel differences, they must ensure that the distribution in both directions contain no evidence of median filtering. Additionally, since pixel values are correlated in both the horizontal and vertical directions, a forger needs to ensure that modifications to the pixel differences in one direction do not create visual distortions in the other direction. As a result, we examine the pixel differences jointly in both directions. We define the pixel value difference pair dij as. Our goal is to fool median filtering detectors by modifying the pixel differences in a median filtered image so that its pixel difference distribution appears to come from an unaltered image. We do this by first parametrically modeling the pixel value difference distribution of an unaltered image and a median filtered image. We modify the pixel difference distribution of a median filtered image by adding specially designed noise its pixel differences. We design the distribution of this two-dimensional noise so that when it is added to the pixel differences in a median filtered image, the pixel difference distribution of the anti-forensically modified image will match. An estimate of the image's pixel difference distribution before median filtering. Let the random variables u and m be the pixel value difference of an unaltered image and a median filtered image, respectively, and n be a random variable representing the anti-forensic noise. Then by exploiting the property that when two random variables are added together, their distributions convolve with each other, where fm, fn, and foo are the distributions of m, n and u respectively. We can see from EQ3 that designing the anti-forensic noise distribution is equivalent to the design of a system. Impulse response. Fn, dj, with predefined input fm, dj, and output foo, dj. The system overview is illustrated in Fig.1. We approach this task by the following steps. We first propose using generalized Gaussian distribution to characterize the distribution of pixel value difference vector d parameters for the generalized Gaussian distribution for both unaltered foo, dj, and median filtered fm, dj. Images are gathered using an image database, and thus we find the relationship of distribution parameters between the median filtered image and an unaltered one. We use the relationship to estimate a plausible unaltered image distribution f, u, dj, given a median filtered one. By exploiting the relation in EQ3, we can design the noise distribution fn, dj, to add to the image. We devise technique to add the noise realization into the image. Finally, our technique is tested against the known detectors over a 50 anti-forensic attack performance. 3. Target distribution estimation. Parametric model of pixel value difference distribution. We propose to model the pixel value difference distribution using a generalized Gaussian distribution. Fig.2 and Fig.3 shows that the generalized Gaussian fits the pixel value difference distribution. Since we care about the joint distribution of the horizontal and the vertical pixel differences, we further propose to model the pixel value difference distribution using a two-dimensional generalized Gaussian distribution. The formula for a two-dimensional generalized Gaussian distribution is given in EQ4:14, where z, a, and a are normalizing constants. In EQ4, d is a 2 by 1 vector. S is the covariance matrix of the random vector and a is a parameter which controls the shape of the generalized Gaussian distribution. The distribution can have different kurtosis by adjusting the parameter a. Parametric estimation of a plausible unaltered image pixel value difference distribution. We make an assumption that the pixel value difference distribution is directionally invariant. In order to parameterize the distribution, we need to estimate S and A. We obtain an estimate of the covariance matrix S and the maximum likelihood estimator for A using the method proposed in 14. In order to increase the stability of the estimation algorithm, we apply a Gaussian filter on the histogram of the image before the estimation. Next, we estimate the parameters SU and O in the unaltered image's pixel difference distribution directly from median filtered image's parameters SM and M. We do this by estimating SU, O, SM, and M from each image in a training database, then we perform a linear regression on these parameters using a least squares fit. For example, using these estimated parameters in our parametric model, we can obtain an estimate of the unaltered image's pixel difference distribution, where F equals DFT F, D. Then Fn can be obtained by using IDFT on Fn. Fn would have small portion of negative parts. Because this is not a system impulse response but a probability distribution, which is strictly non-negative, we project it to the closest set of probability distribution by truncating the negative parts and normalizing the distribution. Ferences. This means that when reconstructing the pixel values from the pixel differences, we need to value of at least one reference pixel. We refer to this pixel as the anchor point. Assuming that we choose the pixel at the location, I, j, to be the anchor point, the corresponding pixel value ej in the anti-forensically modified image is given by ej equals xij. Once the anchor point is chosen, we then modify all the pixels in the ith row using where nh is the noise realization of the obtained from the one-dimensional noise distribution fn using the acceptance and rejection method. Noise attack algorithm. Since the anti-forensic methodology is to add noise to the pixel differences dj, the pixel values must be recovered from the pixel diff agate to the next adjacent pixel xij plus 2 because the reconstruction depends on the value of xij plus 1. As a result, the further that we move from our anchor point, the greater the possible distortion introduced into the image. To mitigate the distorting effects of anti-forensics, we add the following modifications to our algorithm. We partition the image into blocks and select the anchor point for reconstruction to be at the center of the block. Since the potential amount of distortion increases the further we move from our anchor point, we segment the image into blocks and independently anti-forensically modify each block. This prevents each the modified pixel values from drifting too far from their original values. By doing this, the horizontal and vertical distance between any point in the block and the anchor point is no greater than half of the block width. For simulation result, we evaluated the performance of our anti-forensic technique using the UCID15 database, which consists of 1,338 color images which had never been compressed. All the images were first converted to grayscale image before any further processing. The grayscale image was used directly as the unaltered image. For the median filtered image database, the grayscale images were processed using a median filter with support 3. To measure the baseline performance of the SPAM and MFF detectors, we used each forensic technique to test for median filtering in both our databases of unaltered and median filtered images. From these detection results, we found that all three detectors were able to achieve perfect detection, i.e. each achieved a probability of detection of PD equals 100% with a corresponding probability of false alarm of PFA equals 0%. Next, we produced our anti-forensic climatified image database by selecting different parameters for the anti-forensic attack algorithm, and produced corresponding sets of modified image databases. The noise realization limit T was varied between 1, 2, 3, 5, and the correction factor SS was selected to be 0.1, 0.3, 0.5, 0.7, 0.9. Then the performance of the anti-forensic technique was tested against the three detectors. The PSNR between the median filtered images and the anti-forensically modified images was also measured to evaluate how much distortion was added during the anti-forensic modification. In typical forensic settings, there is a high cost associated with false alarms. For example, in legal scenarios it is unlikely that a forensic finding will be allowed into evidence if there is a significant probability that a forgery detection corresponds to a false alarm. As a result, a forensic investigator must typically operate with a false alarm rate less than 20%. From a forger's point of view, it is critical that any anti-forensic countermeasures they use significantly reduce the performance of forensic techniques in this false alarm region. Since a forensic investigator cannot typically perform detection outside of this critical region, the performance of forensic techniques at higher false alarm rates is of less concern. The ROC curves for the spam and MFF detectors are given in Fig. 4 with T equals 3 and SS equals 0.1. The detection rate for the three detectors after the anti-forensic modification is mostly less than 50% in the critical false alarm rate region. Specifically, for PFA 15%, PD is typically under 50%. This shows that our anti-forensic technique is very effective in the critical false alarm region. Also, though our anti-forensic technique alters the pixel value difference distribution, our technique also works for the MFF detector that does not rely directly on the pixel value difference distribution. The PSNR between the median filtered image and the anti-forensic modified image with different T and SS is given in Fig. 5. With a given T, PSNR decreases with smaller SS, while with adjuvant SS, the PSNR decreases with larger T. The larger T and a smaller SS mean that the stronger the modification is. As we can see, most of the parameter combination would result in PSNR in the high 30s. Note that the PSNRs are provided as a reference to show that the images are of sufficient quality. In reality, a forensic investigator does not have access to the original image and can't evaluate the quality loss. All they can do is make a subjective judgment of whether the image appears to be authentic or not. The trade-off between the anti-forensic technique parameters and the visual quality means we can optimize between the visual quality and the attack strength to ensure the attack while preserving image qualities. 5. Conclusion. In this paper, we proposed an anti-forensic technique to fool forensic median filtering detectors that operates by adding anti-forensic noise to an image's pixel difference distribution. To accomplish this, we proposed using a two-dimensional generalized Gaussian distribution to model an image's pixel value difference distribution. We estimated the distribution parameters for both unaltered images and median filtered images, then used linear regression to estimate an unaltered distribution parameters from a median filtered image's parameters. We design our anti-forensic noises distribution so that the pixel difference distribution of an anti-forensically modified image appears to come from an unaltered image. In order to ensure the visual quality of the anti-forensic modification, we proposed several measures for limiting the distortions introduced in the modification. Finally, our anti-forensic technique was tested against several median filter detectors. The results indicate that our anti-forensic technique can fool existing median filtering detectors under realistic scenarios.